Hello students and welcome to the 51st lecture on particle physics. And today we shall be talking about quark confinement. As you know that there are 6 quark flavors: up, down, strange, charm, bottom and top, and these are placed in 3 different generations. Up, down, charm is up, down in one generation, charm is strange in another generation, and top, bottom in the third generation. And the convention is the highest charge particle is put on at the top, and therefore you have U at the top and D at the bottom, charm at the top and S at the bottom, and top at the top and bottom quark at the bottom. Now we have anti-quarks like U bar, B bar, C bar, etc. And then the important concept what we have learned while discussing quarks, that we have not seen isolated quark. We see them only in hadrons, where all baryons are made up of 3 quarks and all mesons are made up of quark anti-quark pair. We have also discussed that we have J by psi meson, epsilon meson and other mesons which are the charm anti-charm state, bottom anti-bottom state, etc. etc. And today we are going to discuss about quark confinement. Now, quark confinement is a fundamental concept in the field of quantum chromodynamics. What is quantum chromodynamics? This is quantum field theory of the interaction of quarks with the gluons. Therefore, this is the theory of strong interactions between quarks and gluons. Quarks, as we know, are fundamental particles that combine to form hadrons, 3 quarks for baryons and quark anti-quark pairs for mesons, and they are never found in isolation. You cannot have an isolated quark moving around here and there. Quarks come in 3 colors. Now, these colors were introduced to save Pauli's exclusion principle, and then we had the experimental evidence that these quarks carry an intrinsic quantum number which we call by the name color, while these colors have nothing to do with the everyday color. You may call it by any name. Generally in the literature they are given by the name red, blue and green, but you may call it by Radha, Mohan and Shyam. You can call it by any other name, but the point is that all the quarks carry some colors. And why this was introduced? Because when we talk about delta plus plus baryon or omega baryon or delta minus baryon, then they are made up of U quarks. Spin is 3 by 2, and that means its projection can be plus 3 by 2. This is made up of strange quarks. Spin is 3 by 2. That means projection can be plus 3 by 2. And projection is plus 3 by 2 means all 3 of them are in spin up states. Similarly, this is made up of D quarks, spin 3 by 2. All 3 of them have got a spin in the upward direction. Now, the important catch is Pauli's exclusion principle tells us that no 2 identical fermions can have all the quantum numbers same. While here we are finding out that in the ground state the quantum numbers are the same. Therefore, to obey Pauli's exclusion principle, it was introduced that actually this is UR, UB and UG, and UR is different from UB and that is different from UG, and these are the internal quantum numbers. But first they were introduced to theoretically understand them and to obey Pauli's exclusion principle. Then in the experiments it was found that really to understand some of the experimental data, you need to have the intrinsic quantum numbers for these quarks. Therefore, the important point is that quarks come in 3 colors: red, blue and green, and gluons carry a combination of color and anti-color charges, whereas all the hadrons are colorless. All the hadrons that those we are talking about, those we have found in nature. Proton, neutron, lambda, sigma, cascade, K plus, K0, K minus, J meson, psi, epsilon meson, whatever you talk about, all those hadrons which you have seen in the experiment, you observe in nature, they are all colorless. They don't carry these quantum numbers. These quantum numbers are there for the quarks or for the anti-quarks. You can say that for anti-quarks, you have anti-red, anti-blue, anti-green, or sometimes you call it by the name cyan, magenta, etc., yellow, something like that. But the combination is such that the object that you see is a colorless object. For example, if we talk about a meson, then it is red and anti-red combination. And then if we talk about baryons, then this red, blue and green, they combine in such a way to give us a white object. Therefore, the important point is this color quantum number was first introduced to save the Pauli's exclusion principle, because till that time no violation of Pauli's exclusion principle was reported. Now, the absence of an isolated quark is attributed due to the nature of a strong force and the way it behaves at long distances. It may be understood as two iron balls connected through a spring made of steel. This is steel. If we leave them, then these two balls will always be separated by a fixed distance and will never come together to form a single object. Whereas if we would like to separate them, then it is very difficult to move them out. Therefore, if we have three quarks sitting here, they are joined with gluons, but this is like a spring mass system, which will say that they are almost like having some constant distance between them, and they are not going further closer to each other. It is like two steel balls, they are connected by a spring. But if you want to take them apart, then you cannot do it, because we have not seen an isolated quark. So therefore, if the quarks move further apart, the energy stored in the gluon field between them increases. Gradually, this energy becomes so intense that it is more favorable for new QQ bar pairs to be created from vacuum, forming additional hadrons and never a free quark. That is the important catch, that we don't have an isolated quark. Still, the phenomena of quark confinement is not very well understood. And why I am talking about all this, because if you recall the Big Bang, the theory of the formation of the universe, what we say that our universe started from a huge explosion. At that time, the density was infinite. The temperature was more than 10 power 40 degree Kelvin, and everything started from a singularity. And then the explosion took place and the things started forming. This we have discussed in the series of lectures. Just in 5 or 6 minutes to recall what we have discussed, that the present theory for the formation of universe is the Big Bang theory, which says that universe started from a Big Bang almost 13.8 billion years ago. At this time, all matter was compacted into a very small distance with infinite density and intense temperature that we call by the name singularity. When the universe was microseconds old and the temperature was about 10 power 13 degree Kelvin, an exotic state of matter existed, which is known by the name core gluon plasma. And you know that currently at the Large Hadron Collider in CERN, experiment is going on to create a microsecond old universe. Because you see, we cannot go backwards in time, we cannot go back in time to see the Big Bang. So, what we do, we try to create the Big Bang, mimic the Big Bang in the laboratory, and see how many particles those generally we find in nature it can exist in that environment, and that means those were there at the time of the Big Bang. For example, string theory people talk about the different uh, particles, electralino, neutralino, Higgsino, etc., etc., which still now have has not been observed. Not a single string particle has been observed in, or we say that these are supersymmetric particles. Those have been observed in the experiment. But that was one of the uh, point to see that whether at that temperature or in that environment we had these particles or not. Then the important point is that if we are going to mimic the Big Bang, this cannot be achieved in one fine morning. And therefore, this experiment where we have the collision of 70 ev protons or ions, then we are creating an environment which is microsecond old, and that means the temperature that exists in that lab, in that environment, is about 10 power 13 degree Kelvin, and that is the state what we call by the name quark gluon plasma. As you can recall, that E is of the order of kT, where K is the Boltzmann constant, 10 power minus 23 joules per Kelvin. This is 10 power 13 Kelvin. You can estimate that what will be the energy at that point of time. And this, if you go further, you want to create, this is a microsecond old universe. That means this is a 10 power minus 6 second old. Similarly, you can have 10 power minus 9 second old universe, and gradually you can go to further a picosecond old universe, a femtosecond old universe, and finally to say a universe which was 10 power minus 20 seconds old. But as you know, as you are going towards this, the temperature is rising enormously, because ultimately what we talk about, the time of Big Bang, the temperature was more than 10 power 40 degree Kelvin, and it is not easy in the accelerators to have that huge amount of energy. Therefore, currently we have that 14 TeV of center of mass energy. Now after 10 years, 20 years, you will have more energy. But to have this order of increase in temperature from 10 power 13 degree Kelvin to 10 power say 18 degree Kelvin or 10 power 21 degree Kelvin is not a joke, and that would take lot of time for the scientist to create an environment which will be more closer to the point when the Big Bang took place. But what the scientists are doing, scientists are trying to understand what had happened at the time of Big Bang. But this is a slow process. It's not easy to create that amount of energy in the laboratory. As you must know that at CERN, where this colliding machine is working, the circumference, the collider is moving through a distance of 27 kilometers. Therefore, if you want to have more energy, that means that you want to build machine which is say of 100 kilometer or 200 kilometers or 500 kilometer radius, and that is not very easy to get, and that is why it takes years, decades and decades to build a high energy accelerator beam. And but the point is we want to mimic the big bang, and we are going from right hand side to the left hand side in this picture. As you can see, presently we are here when the universe is 13.8 billion years old, and we are going towards the big bang. And that means we want to see that what presently the picture which I am telling you, that universe is microsecond olds, the temperature is about 13 degree Kelvin. Then when the temperature was 10 power 15 degree Kelvin, the universe was 10 power minus 10 seconds old. Then we are talking about the temperature when the temperature was 10 power 28 degree Kelvin, universe was 10 power or minus 36 seconds old. And then the temperature was more than 10 power 32 degree Kelvin, and the time was 10 to the power minus 44 seconds after the Big Bang. Therefore, this is the gradual process from right to left that we want to go, and we have moved really in the last 50-60 years. We have tried to understand the different regions, but this is on the right hand side. If you want to go to the left hand side, we have to create more and more energy to mimic that those situations, and to see that what could be the new particles, the exotic particles, those particles which were formed during the Big Bang, but they do not exist now. But the point is, we are talking about the Large Hadron Collider at CERN. What I am telling you, that there is an LS detector, for example, which is going to record, or which is recording the signatures of quark, gluon, plasma. Okay, there are theoretical papers and all that what are the possible signatures of quark, gluon, plasma in the laboratory. And that means we want to see that when the universe was microseconds old, what was the real physical situation. And therefore we have the Big Bang, then we have the quark, gluon, plasma, left to right. The temperature is about 13 degree Kelvin, and universe was microsecond old. Then when the temperature became 10 power 12 degree Kelvin, the time was 10 power minus 4 second old universe. And then low mass nuclei, when the temperature was 10 power billion degree Kelvin, and the time was 3 minutes old. Therefore, the low mass nuclei we have discussed in the class were formed about 3 minutes after the Big Bang. Now, this quark, gluon, plasma represents a phase of extremely high temperature. We are seeing that this is about 10 power 13 degree Kelvin, and energy density where quarks and gluons become deconfined and move freely. We have discussed earlier in the lectures that quarks combine to form hadrons, and there are no isolated quarks. However, as the temperature and energy density of the universe increases, such in the extreme conditions just after the Big Bang, the strong force becomes weaker at short distances, leading to the formation of a hot and dense soup like state known as quark, gluon, plasma, or in literature it is better known as QGP. And then we talk about the signatures of QGP. One of the key features of QGP is its low viscosity and high thermal conductivity, which makes it behave like a perfect fluid. Now, the other important point that which I am talking about is the screening and anti-screening of the charges. And I am talking about first the electron. As you know that in field theory, electron does not remain an electron all the time. An electron emits a virtual photon that gives rise to electron-positron pair, which again give rise to photon, and that again give rise to electron-positron pair. Therefore, you have an electron which emits a photon. This gives rise to electron-positron pair. This again emits a photon that gives rise to electron-positron pair. Therefore, what happens actually, that electron, this physical electron, is surrounded by the positrons, because these are the oppositely charged particles. These are surrounded by the this electron which was originally there, and then there are electrons at larger distances because you have all the time electron positron pair. Therefore, if you are far away from this region, then what is happening? These positrons are eclipsing the original charge of the electron. You are not seeing the original charge of the electron. You will be able to see this charge only when you will be able to penetrate this cloud, and that is known by the name screening of the charge. Therefore, when you are far away, you are observing a less amount of charge, and when you are penetrating this cloud, then only you are able to observe the exact charge of the particle. Now, to understand this, if we consider two particles having charges Z1e and Z2e separated by a distance r, then the force between them is given by the well-known Coulomb's law, and it is given by 1 by 4 pi epsilon naught Z1e times Z2e upon r square. However, if the distance between the two particles become very small, then quantum mechanical effect comes into play. In quantum field theory, an electron is just not an electron. As I spoke about it, it can emit a photon that can subsequently annihilate into electron-positron pairs and so on. These quantum mechanical effects can be described as the polarization of the vacuum by a sea of electron-positron pairs in the vicinity of the electric charge. Like, for example, an electron that we are talking about. Say, for example, if we consider an electron, then at very short distances, an electron is immediately surrounded by a cloud of charges which is polarized in such a way that the positive charges are closer to the electron and the negative charges of the electron-positron pairs is separated by some distance. Thus, an electron is screened by the presence of positive charges, and if we are at far distance, then the exact charge of the electron cannot be determined. For this, we will have to move closer to the electron and penetrate the cloud of positrons that screens the electron's charge. And therefore, this is the real charge of the electron on the y-axis. This is the distance. If you are at far distance, you are seeing a reduced charge, and then when you are going closer to the electron, you are penetrating the cloud, then only you are seeing the actual charge of the electron. Therefore, thus by going closer to the electron, one is able to determine its exact charge. This is known as screening of the charged particles. Now, when we talk about the quarks, just now I have spoken about the fact that quarks come in three different colors, and then these gluons, they carry color themselves, and there are 8 types of gluons. We have 6 types of quarks. There are 8 types of gluons, and in the case of quarks, a quark is also surrounded by quark anti-quark pairs in the same analogy as that of the electron, but there is an additional effect as the gluons, the mediator of strong interactions, carry colors and the self-coupling of gluons happens. For example, you cannot have self-coupling of photons, but in this case, in QCD, if I am talking about a quark, this emits a gluon. This gives rise to a quark anti-quark pair. This is giving us quark, the gluon, quark anti-quark pair, and all that the similar to what we have spoken about electron. But because these gluons in QCD, self-coupling of the gluons are possible because they are also carrying colors. Therefore, besides this diagram, you can have such type of diagrams. Self-coupling of the gluons is possible. Therefore, a picture will be similar to the picture what we drew for the electron, but there will be an additional picture that will arise because of the self-coupling of the gluons. Now, because of this additional figure, what happens? A quark is surrounded by the quarks itself, only a few antiquarks, and then antiquarks are at a larger distance. Then there are a few quarks also. Therefore, when you are at a further distance, you are seeing an enhanced charge of the quark. It is only when you are going closer to this quark, you are finding the actual charge of the quark. Therefore, if you notice, here we are talking about the fact that if you are at a larger distance, then we are observing a reduced charge of the electron, and when we are penetrating this wall of positrons, we are finding out the actual charge of the electron, which is much higher in magnitude than the what we were observing here. But in this case, what is happening? Because of the self-coupling of the gluons, we at further distance we are observing a more enhanced charge than when we are penetrating the cloud and coming closer to the quark itself. Therefore, we have one picture like this, the other picture are like this, and then the net effect of these two pictures is that we have anti-screening, and therefore if we talk about the distance here and the charge like in the previous case, then at larger distance we are observing more charge, and then we are getting closer, we are seeing a charge which is in reduced strength, while in quantum electrodynamics it is other way around, that here when we are at a larger distance, we are seeing screen charge, less charge, and when we are moving closer, penetrating the positron cloud, we are seeing the actual charge. Therefore, there is a difference between quantum electrodynamics picture and quantum chromodynamics picture. Remember, quantum electrodynamics is the quantum field theory of the interaction of charged particles with the photons, while quantum chromodynamics is the quantum field theory of the interaction of quarks with gluons. Okay, so therefore the presence of the additional diagrams reverse the familiar results of quantum electrodynamics. In QCD, a red quark is more closely surrounded by red quarks. Thus, if we are probing a color charge from a larger distance, then the observed one will be larger than the case when we penetrate the cloud of red charges and reach closer to the original red quark. This phenomena is known by the name anti-screening of the red color and is referred to as the asymptotic freedom, meaning by that for very small separations, two red quarks interact through color fields of reduced strength and approach a state where they behave essentially a free, non-interacting particle. Therefore, there is a big difference between the picture of quantum electrodynamics and the picture of quantum chromodynamics. Here we have, in the earlier case, when we had started this lecture, we talked about quark confinement, and here we are talking about the asymptotic freedom. This is what I am discussing, that a red quark is surrounded by the red quarks because of the self-couplings of the gluons, and if you are at a further distance, then you are finding out a greater strength of the charge than when you are penetrating this cloud and coming closer to the red quark, for example, or this will happen with a green quark or any other quark that you talk about. Therefore, this is what we call it by the name asymptotic freedom. Therefore, this is the region, the right hand side is the confinement region and the left hand side is the asymptotic freedom region. So therefore, these are the very small subtle concepts in particle physics when we talk about the quarks. And then in the next lecture, I am going to tell you how to calculate the charge of the proton, charge of the neutron, charge of the mesons magnetic moment of the proton, magnetic moment of the neutrons, mass of the proton, mass of the neutrons, or in general baryons and mesons, using the Quark model. Because if we believe in the Quark model, then we should also get the observables, because observables are the actual answer to the problem, because charge of the proton is +1 in units of electronic charge, charge of neutron 0 in units of electronic charge, magnetic moment of the proton 2.79 nuclear magneton, neutron -1.91 nuclear magneton. So therefore, using Quark model, we shall try to observe the or get the real numbers for the observables corresponding to the baryons and mesons. Let us stop here, and we shall discuss these concepts in the next class. Thank you.